OK，大家好。我会讲中文一点，但是我讲的不太好，所以我现在要说英文。So, okay. So what I wanted to go through today is kind of go through some of the ideas of why I think blockchains are interesting and what makes them interesting. And particularly why public and open blockchains are interesting. What makes what makes them interesting? What makes them different from the other kinds of systems that we've used and built over the last few years and centuries and millennia, and what makes them similar to some of the other systems that we've built and used, and go in a bit into what kinds of applications I think blockchains could really make sense for, even going beyond very obvious ones like cryptocurrencies. So, to start off, what is a blockchain? Now, I mean, there's 50 definitions of what a blockchain is, but this is the one that I've been using more and more lately. So I tend to think of a blockchain as a decentralized network that has a memory. Right? So this is a definition that has two parts to it. And you might notice that it doesn't talk at all about, chains, hash graphs, Merkle trees, blocks, how transactions work, cryptography. It just mentions kind of what I think are two very important properties that distinguish it from many other systems that we use. So there are many kinds of decentralized networks, right? Who here has used BitTorrent before? Okay, I assume in reality it's about twice as many people. So Skype in its very original early form was also a much closer to a peer-to-peer messaging network, and right now they've introduced, especially after they were bought out by Microsoft, I believe they've introduced more centralized servers, but it still has peer-to-peer elements to it. There are things like FireChat for decentralized messaging. There's plenty of different decentralized messaging protocols that have been out there for the last 15 years or so. More recently, there are things like Bitcoin. Who here holds Bitcoins? Cool. Namecoin. Who here holds Namecoins or has a domain registered on Namecoin? Okay, so not every blockchain application is equally successful. Who here has a domain on ENS? Okay, see, now the first mover doesn't always win. There are now you can clearly kind of feel probably in your minds that the things at the above the dotted line are decentralized networks, and the things below the dotted line are also decentralized networks, but they feel like different kinds of decentralized networks. And you might not entirely see what makes them so different beyond maybe the fact that the things below the line are blockchains and the things above the line are not, but that's exactly what I wanted to get into. So, yeah, the second category, things like Bitcoin and Namecoin and Ethereum, is not like things like BitTorrent and Skype and FireChat. So why? This is the second part of the definition of a blockchain. Does everyone remember what the brain stands for?
Memory.
Memory. Okay. So, what do we mean by memory? Well, we can think about memory in context of the very first blockchain application, Bitcoin. And Bitcoin, in the white paper, was described as a peer-to-peer digital currency. And the white paper described the problem that the blockchain was solving as the double spending problem. Now, what is the double spending problem? Well, it might at first it might seem reasonable to think, well, if we can have a decentralized network for sending files, and we can have a decentralized network for sending messages, why can we not have a decentralized network for sending digital money? So, here is the challenge. Let's suppose that I have 100 digital Taiwan dollars, and I send these 100 digital Taiwan dollars to Alex here on the left. Then I then copy the file that I had that contains the 100 digital Taiwan dollars, and I send another transaction that sends the exact same 100 digital Taiwan dollars to someone else on the right. Now, either one of those two transactions is totally valid by in isolation, right? If the first transaction that I sent, I had 100 digital Taiwan dollars, I exercised my right to send them. The second transaction that I sent, I had 100 digital Taiwan dollars, I exercised my right to send them. But if you have a system that just looks at every transaction as a thing by itself, then it will accept the first transaction, it will accept the second transaction, and what have you done? Well, you've converted 100 digital Taiwan dollars into 200 digital Taiwan dollars. Now you might think, oh yay, this is great, yay, post-scarcity utopia, no more poverty. But if we were to do this in reality, the digital Taiwan dollar would hyperinflate faster than Zimbabwe. So, obviously we cannot have this ability to convert 100 into 200. And so, what do we do? Right? Now, what we actually want is we want a system where the first transaction that I send succeeds, and the second transaction that I send fails. So we want a system where it actually keeps track of the fact that at this point in time, I have the money, then I use the money, and at the later point in time, I do not have the money. And so the same transaction that was valid earlier in the context of what was kind of the state of the system at one point in time is no longer valid in the context of the state of the system after I send the first transaction. So this is memory. Now, memory has very many different use cases, but the very simplest use case to think about is kind of who did it first, right? So in this case, who did it first is who received a coin first. But there are other possibilities. So let's say, for example, that you want to make a domain name system on the blockchain. And let's say, basically try to take the existing domain name system, just replicate it in a decentralized way. Now, let's say I said I want to register Ethereum.org. And I did this in 2013. And in this kind of system, that would entail sending a message that would say, I want to register this domain. Now, let's say right now, someone else wants to try to register the same domain in order to, let's say, trick users into visiting their site instead. Well, they would go through the exact same process that I did, and they would also send a request to register the domain. Now, what would anyone who joins the system after that point in time see? They would see that, number one, there is a message sent at some point in time of me registering the domain. And there is a message sent by someone else at some point in time also registering the domain. A system without memory would have no way of distinguishing which one of those two was sent first, and so which one of those two actually should have the domain. If you have a system with memory, then you can solve this. Entering into a financial contract, or even just accepting an offer. So let's say I want to make an offer to trade 100 digital Taiwan dollars for 40 digital, let's say 0.01 Ether. And I push out this offer, and let's say two people both try to accept it. Now, clearly, I do not have enough of these digital dollars to satisfy both of those offers. And so the first needs to succeed and the second needs to fail. Another example, what if I make an offer, then later on I change my mind and withdraw the offer, but at the exact same time someone sends a transaction to claim it. One of those two operations needs to succeed first. So this idea of resolving who did something first when there are two different operations that are incompatible with each other is one use case of memory. But really there are many different use cases of memory, right? And this isn't something that we normally think about much in a kind of traditional centralized setting, because in a traditional centralized setting, well, the question of who actually does the remembering is easy. It's, like some guy over there, there's a server, right? If there's some company, it has a computer, on the computer has a hard drive, and the hard drive keeps track of basically how much money it has, right? So if you look at, there's plenty of digital currencies that already exist, right? Type A subway cards. There's a server somewhere that just keeps track of how much I have on here. If that server got burnt down, then no one would be able to tell if on here I had, $50, $900 or 900 million. So Now, in a kind of centralized context, we know what that looks like, and this is something that we've worked with for a while, right? Whether it's a digital record, whether it's a physical record on paper, whether it's like some record that's plastered in the middle of like some medieval town square, it's basically the same sort of thing. Now, in a decentralized context, having a decentralized notion of memory is harder. And there are kind of good computer science theoretic reasons why this is the case, right? So there's one very simple thing called the CAP theorem, which actually sounds a lot scarier than it is. And basically it says you can't, if there is a partition, you can't have consistency and availability at the same time. So what does this mean? Well, let's suppose that we over here are all part of a network, and let's suppose that right down the middle over here there is an earthquake. And this entire room, suddenly there's a big fissure, and these two halves of the room are 500 kilometers apart. Let's say I am the only person that can still talk to both halves. In the first half, I take my 100 digital dollars and I send them to Alex. In the second half, I take my 100 digital dollars and send them to someone else. Now, really there's only two possibilities. One of those possibilities is that both of those transactions get accepted, and your kind of world splits into two halves, and these two different halves have two completely incompatible realities. Or at least one, or probably both of those transactions just fails and goes nowhere. So you can't have availability, transactions always succeed, and consistency, the world agrees with itself at the same time necessarily. And this is just one of the reasons. There are many other reasons why kind of memory in a decentralized context is actually a fairly tricky thing to achieve. Now, there have been a lot of kind of academic systems developed in the 1980s and the 1990s that achieved it in the context of one particular model. Right, so this is something called Byzantine fault-tolerant algorithms. So what are these algorithms? Basically, take 5 people, or take, I don't know, like 50 people, and they engage in this algorithm where they all kind of talk among themselves, and they engage, and they can accept transactions, or just operations representing anything, and they try to agree on which transactions or which operations kind of came in and got accepted in what order. And the algorithm has the property that as long as at least 2/3 of the people participating are online and are honest and kind of have not been corrupted, have not been hacked, are not acting maliciously, then the system works and everyone agrees. But if there's less, at least 1/3 of the participants suffer some kind of problem, then it's either consistency or availability could break, either the system stops working or the system disagrees with itself. And if you have enough people, then it's actually very unlikely that more than 1/3 of them actually, or more than 1/3 of these computers actually end up breaking at the same time. But so this existed for a while, but this did not turn into a decentralized peer-to-peer digital currency. And you have to ask why, right? Now, the answer why is actually, I would say, a fairly subtle one, right? The answer basically is that, first of all, you have to choose who the 50 people are. If you choose the 50 people incorrectly, then you actually have a system which is totally not decentralized. If you choose 50 people, and they are all Microsoft employees, then the CEO of Microsoft can probably threaten to fire all of them and convince at least a third of them to do whatever he wants them to do. If all 50 of these people are even in one single country, then the government of that country can put them in a prison camp and make at least a third of them do whatever it wants, or at least get almost all of them to not do anything. If these 50 people end up being 50 different, even like 5 or 7 different banks, well, even 5 or 7 different banks might collude with each other. And historically, they have colluded with each other to do things like fixing interest rates. So, this is the first problem, right? It's hard to come up with this kind of set of 50 people that everybody trusts, right? Now, the second problem is problem of incentives. So, let's say you have been selected to be one of these 50 people. Why do you even participate? Right? What kind of, what is your incentive to figure out, how to join the system, figure out why the system is worth participating in, actually participate in it, keep the computer running 24/7, participate in the consensus algorithm. If your computer goes offline, try really hard to make sure it gets back online. Why would you do this? So, as it turns out, both of these problems were problems that Bitcoin successfully solved. Now, how did Bitcoin successfully solve both of these problems? Well, basically, it's this trick that I call cryptoeconomics. And the idea is that we combine together cryptography, decentralization, and economic incentives all into one common package. So, how does this work, right? So, if you look at a system like Bitcoin, you have basically, you have this concept of miners, right? Where anyone who has a computer can, or anyone who doesn't have a computer can expend resources and get a computer. And with your computer, you can run these kind of mathematical computations. Now, they're very expensive and they're basically useless mathematical computations. But the purpose of these computations is basically to prove that you have a computer. And that you're not just, like some guy pretending to have 10,000 computers that are actually on the same machine, right? Like if you try to pretend you have 10,000 computers, then you actually have to solve enough math problems to keep convincing the system that you have 10,000 computers, and there's no way to do this without having either 10,000 computers or something equivalent. So basically anyone can download the software package and run it on some computer. And this software package basically uses like 100% of that computer's CPU to keep on proving to the network that this is a unique computer that is part of the network. Then part of this algorithm has a rule that basically if you run this algorithm, you at random intervals create something called a block. And creating a block gives you the right to pick out some set of transactions that nodes or anyone around in the network has sent that have not yet been included, and put them into this kind of package and broadcast them around the network. Now, every block has to also say what is the kind of the previous block that they know about, right? So everyone runs this algorithm, and at some point, some node randomly makes a block. Then at some point, some other node makes a block that points to that block, and so on and so forth. So you have this chain of blocks, which is called a blockchain. Now, first of all, who is this kind of, in some ways, this is a fault-tolerant consensus algorithm, right? If any one of these computers shuts down, well, there's plenty of other computers that will keep going. If one of these computers gets hacked, and it tries to do something like creating a block that references some block that everyone else agrees is not part of the chain, then, well, there's the longest chain rule, right? Even if some portion of the network disagrees with the rest of the network and tries to make their own chain, well, the chain that everyone else is working on is bigger. It has, it's going to create more blocks, it's going to create bigger blocks, and that's the chain that everyone will accept, right? It's basically kind of like a simple majority rule system. So it's a fault-tolerant consensus algorithm, but who are the 50 guys participating? Well, here's the thing. The system never specified which 50 guys it is. Basically, anyone in the world who has access to a computer and has access to the electricity to burn can join the system and become one of the participants. Right? So this is the first part, and that solves the first problem. So you don't need to trust that the 50 people are chosen correctly, because the 50 people were chosen in such a way that literally anyone in the world can join the system, and so there's no way to kind of for anyone to try to kind of bias it toward basically some specific group that they think they can corrupt. Now, here's the second part. Why would anyone participate? Well, the answer is that in the Bitcoin protocol, there is a rule, and that rule says if you create a block, and this block becomes part of the chain, you get a reward. And this reward is currently 12.5 Bitcoins. Now, if you create a block, and this block does not get accepted by the network, then you do not get a reward. Right? So you have this, the purpose of this incentive is, first of all, to encourage people to participate and to encourage people to participate correctly, and particularly to compensate people for the electricity that they're burning by using this kind of very expensive process for proving that they actually have some number of computers. So what you actually have is something that's very philosophically clever. You have a system whose security is backed by economic incentives, where those economic incentives, the cryptocurrency, are themselves defined inside of that system. So you have this interesting kind of self-supporting structure that has these two parts, right? One part is the database, basically the system in the block, the fact that the blockchain has this memory of who has how many coins at some particular time. And the second part is the kind of algorithm that actually maintains the blockchain itself. The algorithm depends on the memory, because the memory contains the currency, and the currency is what motivates people to participate honestly in the algorithm. And the currency itself depends on the algorithm for the security of the database. So you have these kind of two structures that depend on each other, and what you have as a result is a system that can get bootstrapped from scratch and create this peer-to-peer digital currency that exists. It is quite reliable, as reliable as many other financial systems, all without relying on any existing currency, any existing root of trust, any existing intermediary, or any existing centralized institution. So this is kind of the core and where it all started from, right? And so, why is decentralization actually interesting, right? So, there's a few reasons for this. So the first reason is, of course, security, right? So you have these kind of Byzantine fault-tolerant consensus algorithms, and things like Bitcoin's proof of work and Ethereum proof of work and so forth kind of count as one, and they let you create systems that you cannot break into unless you can basically hack into or kind of overpower a very large number of computers at the same time. And you have cryptography that actually protects the transactions. So you have cryptographic algorithms that let you prove that this particular transaction actually was approved by me. So another kind of very important part of why decentralization is interesting is this idea that it reduces barriers to entry. So what do we mean by this, right? So for basically, think about what an application running on something like Ethereum can give you. Now, let's say that you wanted to build, let's say, an online voting system, and you wanted the online voting system to have the property that, first of all, it's secure, and it can't get hacked, and that it's guaranteed to actually give, basically the correct result. So it's guaranteed to give the result that actually is the sum of what everyone voted. Now, let's say you try to do this on just a regular computer. What would be the cost of you doing something like this? Now, you could obviously spin up a VPS, but then, well, that VPS could go down, or the company that's running the server could get hacked. It could get hit by a denial of service attack. And why would other people actually trust your system? That's also not necessarily particularly clear. So the cost of solving all these problems in a traditional setting can actually be pretty substantial. What is the cost of solving this problem by building your application as what's called a smart contract, as a computer program that runs on the Ethereum blockchain? The answer is something like 50 cents. So this is one of the ways that blockchains reduce the barrier to entry, right? They create infrastructure that gives a fairly high level of security and does so in a way that's much cheaper than anything that was available before. So for developers, there's this idea of kind of zero infrastructure, that you can build applications. In building applications, it's like fire and forget. Once you build the application, assuming everything with the application works, theoretically you do not need to touch it, you do not need to maintain the infrastructure, everything kind of operates autonomously for as long as there are users of the system. This is a kind of inclusiveness that I think is very valuable, right? And this is a point that I often like emphasizing. Like basically, a lot of people like to talk about blockchains for like financial inclusion and things like banking the unbanked. Well, here we're not just talking about banking the unbanked. Here we're also talking about basically helping the unbanked become bankers, right? So like if you're in some less privileged country and you are an entrepreneur and you want to build some kind of peer-to-peer insurance system, well, what are your costs? First, you have to build the thing. Then you have to connect it to existing financial systems. Then you have to basically convince society that your application is a thing that actually can be trusted and that you're not going to run away with people's money. And we have different ways of doing this. This could consist of just having a reputation, going out publicly, showing yourself, getting a government license, like just advertising, like getting like credible people to say that your thing is legit. Like there are ways of doing this, but they tend to have fairly high social costs. Now, if you build a platform on a blockchain, then you can design your platform in such a way that basically a lot of the safety properties are instead technologically guaranteed. Basically, instead of telling people, hey, I'm some guy, I am making a peer-to-peer insurance platform. Please send your money to me. I promise I will not take it. Instead, you say, oh, I built this peer-to-peer insurance platform. Here is the computer program. You can send your money into this computer program, and by the way, here is a mathematical proof that shows that this computer program is not going to steal your money. So there are still hurdles with the second approach, but because you've kind of moved at least part of the trust gathering problem from the social realm into the computational realm, the costs become reduced quite a bit. So another one is just cutting down trust barriers between in kind of larger scale organizations or larger scale applications. If you want to build an application that exists only between Microsoft employees, then trusting those 50 Microsoft people to run the thing might actually be not that bad an idea. Microsoft employees in some city might actually know a lot about each other and might trust each other quite a lot. Now, let's say you want to build an application that would allow people to interact between every country in the world. And let's say you have like some startup that's based in Guatemala. Well, okay, you have a startup that's based in Guatemala. Why should people on the other side of the world in Kyrgyzstan trust it? So, well, what can people in Kyrgyzstan trust? People can trust that, number one, cryptography and math works in Guatemala the same way it works everywhere else. And number two, that people in Guatemala follow like economic incentives and like money. So if you design a system where the security of the system is based on crypto economics, is based on like economic incentives and kind of basically cryptography and mathematical logic, then you have a system that can kind of go to much larger scales and kind of go across social boundaries much more easily. And this isn't just theoretical, right? This is like there have been, even within the blockchain space, right? There have been at least 2 companies I know about that have basically originally were taking a kind of semi-centralized approach where they were trying to build what's called a consortium chain, basically using one of these older Byzantine fault-tolerant algorithms and making a network between 5 different companies. And they initially thought, well, this is going to be very efficient. We don't have very many computers in our network. It's nice. We can kind of control it. And then later on, they found out that getting their first customer, getting their second customer is fairly easy. But then once they start expanding more, they get this problem that, well, if, let's say, the first, this is some company, and the first major company that they partner with, let's say, is Samsung. Well, then, let's say they try to expand, and they go to Taiwan, they go to Japan, and, they try to get more partners in other places. Well, the feedback, the kind of impression that's very hard for them to get past is, well, aren't you just asking us to join Samsung chain? Aren't you just asking us to become vassals of yourself and Samsung? Basically actually credibly showing that you're creating a system that is going to treat them fairly in the same way that it treated the first participants. And this is the sort of thing that centralized systems in a lot of ways have hard times doing. And these are social costs, right? These are costs that have to do with basically frictions between people and frictions involving limits between people's two people's ability to basically trust each other or predict each other's behavior or even just understands what motivates each other. And social costs are something that is fairly hard, they can be fairly hard to estimate, but they are large, right? The idea behind a lot of kind of the public blockchain story is that decentralized solutions and computationally decentralized solutions like public blockchains tends to have substantially higher computational costs than other approaches, right? So in Bitcoin, every node in the network has to download every single block and verify every single transaction. In something like Ethereum, that's also the case. In future versions of Ethereum, it'll be less the case, but even still, you'll probably have 1,000 computers basically checking over each other's work. And on top of that, you have cryptography. On top of that, you have Merkle branches, and so on and so forth. So decentralized solutions tend to have higher computational costs and higher kind of total IT costs than other approaches. But they take on this burden in order to achieve lower social costs. And here's a fact about, basically the kind of relative importance of computational costs and social costs over the last century. So, basically, even with 25,000 computers checking everything, these days computers actually are fairly cheap. So so this is kind of one of the kind of big core ideas behind what I see as the public blockchain pitch. Now, what can you do on top of blockchains? So one of the interesting things that you can do is this idea that's called a smart contract. And a smart contract, there are many different definitions of this, and the kind of narrow sense definition is a smart contract is a computer program that lives on a blockchain that directly controls digital assets. So basically, it's not like, in the old world, assets had to be controlled by some guy. In the new world, assets can be controlled by a computer program. And it would be only the computer program and nothing else that would have authority to decide under what circumstances it sends how much of those assets to whom. In the broad sense, a smart contract can be an application that sits on a blockchain that accepts transactions and executes its business logic according to certain rules. Nick Szabo in 1994 came up with this fairly interesting analogy for smart contracts where he likened them to vending machines. A vending machine is a device implemented in physical hardware that enforces the terms of an agreement. What are the terms of the agreement? You put $50 in, bottle of water comes out. You do not put $50 in, bottle of water does not come out. You put $150 in, 3 bottles of water come out. Right? Fairly simple. Now, of course, in the physical world, a vending machine, there are limits to a vending machine's security. If you really wanted to, you could take an axe and you could break a vending machine, and you would be able to pay $0 and get 100 bottles of water out. But this is difficult, and breaking a vending machine is the sort of thing that would lead to fairly loud noises and possibly the police putting you in a free hotel for some time. Now, even still, it's limited, right? But in the digital world, the idea would be that a smart contract is like a digital vending machine. It is a device which is implemented as a computer program in the digital world, which, once again, enforces the terms of an agreement that have to do with digital assets, but the security is basically close to infinite, right? The nice thing about cryptography is that cryptography is the one kind of area, field in the 21st century where defense is millions of times more powerful than offense. Even any regular person has the ability to use cryptographic tools that have the ability to protect their data even from some nation-state actors. You know, the physical world doesn't work this way, right? You have one bunker, well, 100 people with guns can blow it up. In the digital world, you know, cryptography actually is like really effective and strong and gives you the ability to create these kind of digital lockboxes that are cheap to make and easy to break if you're, or easy to open if you're supposed to, but extremely, extremely difficult to open if you are not supposed to. And this kind of cryptographic asymmetry, plus the crypto-economic security of a blockchain itself, is the kind of environment that it makes sense for a smart contract to live on top of. So, this can be used for a lot of different things. And there are lots of different projects that are kind of building things on top of smart contracts. So like there are one of the kind of very simple canonical uses of a smart contract is just basically like trading one thing for another thing. And there are a lot of use cases for this for things like just trading financial instruments, right? If let's say you want to buy a bond, like a digital bond, then the bond itself can be written as a smart contract, and the rules of smart contracts can say that the bond only activates once you actually put the money in. If you want to trade one type of token for another, or you spend some tokens to register a domain, trade some tokens for an asset, then you can write a computer program that holds one of the assets, and the code of the computer program would say that it only releases that one asset when that contract receives the other asset. So there are things like that you can do. Now, public blockchains have a lot of these kind of financial applications and more broadly applications that have to do with like tokens and things that are valuable in various ways. These tokens don't necessarily have to be kind of money in the strong sense. So in the top right, you have a refugee program that's part of the UN World Food Program, and they basically just use Ethereum internally to keep track of payments going to refugees inside of a kind of closed special purpose system that basically it gives them tokens they can use to buy to kind of get access to like food and kind of like other commodities for their survival. But even outside of things like that, there are other things that you can theoretically use a blockchain for, right? So you could use them for things like keeping track of like information about identities. You can use them for keeping track of things like like has this particular product already been opened? You can create kind of a digital equivalent of tamper-proof seals that are much harder to tamper with. You can create systems where, like, if you have some kind of cryptographic key that you use to sign messages, then you can use the blockchain as basically a way of storing, like, is this key still valid? Has the user decided to revoke the key yet? And the blockchain can be used as a kind of database where someone can check the blockchain and actually see and actually verify that like some particular cryptographic key has not yet been revoked, right? So people sometimes also talk about the blockchain as providing kind of proofs of existence. So there are a lot of these kind of fairly simple blockchain timestamping applications where if you want to sign some kind of legal document, then you could use cryptography to digitally sign it. But then you could also kind of embed a hash of the document into the blockchain in order to prove that the document was signed, that the document existed before some particular point in time. The more interesting thing the blockchains often give is proof of inexistence. So proof that some particular resource, some particular object is still active in the sense that it has not yet been turned off or consumed. Or that proof that this coin has not yet been spent, right? So there's applications of this kind of idea in a lot of industries, whether it's like pharma, supply chain, various identity-related things. And there's interesting even things like online voting and online polling. Like blockchains are not the best technology for every single use case, but there are lots of use cases where like you actually can use blockchains to increase security in a fairly decent way. So there are a lot of various things like that, right? So, and there are basically hundreds of applications that people are trying to build using this kind of paradigm. So right now, even though cryptocurrencies are growing very rapidly, and as I saw walking past the laptop of one of the people in this room, Bitcoin is around something like $9,600. And the total cryptocurrency market cap passed 300 billion. That ultimately those numbers just basically represent hype and excitement, right? As far as actually applying the technology and using it to kind of build things that go beyond just payments and storing value, we are still at an earlier stage. But there are lots of people that are very actively thinking about these kinds of problems, thinking about how best to use blockchains, working on new forms of cryptography that can be combined with blockchains to provide kind of better security and better privacy, and lots of other interesting applications. And if this is the sort of thing that seems interesting to you, then I'd encourage you to look into it. Thank you.
OK， 是否有学长姐想要提一些问题跟Vitalik来做一下 ？OK， 好，那旁边有麦克风，可以直接，还是？
My question is, will the Ethernet need the hardware to accelerate the transaction?
So in a lot of cases, not that much. Basically because in a lot of cases, it's bandwidth and storage that are the main limitations. But once we start looking at combining together blockchains with advanced forms of cryptography, so things you might hear about things like zero-knowledge proofs, then a lot of these newer forms of cryptography give you very powerful privacy properties, but they do so at the cost of those transactions actually taking a very long time to create, right? So there's a new cryptocurrency that was released about a year ago called Zcash, which has the property that it has much stronger privacy than Bitcoin or Ethereum, at least up until some of our very recent changes. And it's the problem that Zcash has is that one transaction, even after a lot of upgrades that will only come to life next year, will still take about 7 seconds to create. And so this is the sort of thing that specialized hardware actually can do a very good job of accelerating. Yeah.
Anybody?
So this part is rather not covered in your presentation, but I'd like to ask that from the beginning of Ethereum, Switzerland is an important country. The foundation is state located in Switzerland, and also ICOs, a lot of ICOs located in Switzerland. So in your opinion, is there an ideal way that at this phase sovereign countries should interact with cryptocurrencies?
So yeah, I mean, Switzerland definitely is a very favorable legal environment for a lot of these projects. I mean, more recently, Singapore has been catching up quite a lot as well. I mean, in part because Switzerland is very expensive in a lot of ways. So it's probably those are the two places that have been kind of more successful as being the base for these projects. For countries in general, I mean, I think if there were more countries that adopted a kind of a friendly role to these blockchain projects, then I think that would be obviously a positive thing. Though at the same time, it can try to look beyond just kind of being a place that people register a legal entity at and actually look at, where can these blockchains where can these applications be used in their country, inside of their government, in international commerce, and see if there are ways to kind of facilitate those kinds of applications. And there have been a few examples of that happening as well. So, for example, the central banks in England and Singapore, in Russia, and a few other places have all expressed a lot of willingness to look at things like central bank issued digital currencies, look at various other blockchain applications. They've written quite a lot of reports about it. And they have been starting to do test projects to try to see what an implementation would actually look like. So this is something that I would definitely encourage people to look at, and I would even encourage Taiwan to particularly to look at it, because I know it has an existing history of gov.tw. There's a lot of very positive digital democracy and government things happening here. There's also kind of applications in just every other industry. So for basically things if you look at the Southeast Asian context particularly, for example, there's a lot of applications that are trying to do remittance. So trying to do basically using cryptocurrency to do international either public blockchain cryptocurrencies to facilitate international payments from there's one that's doing from Korea to the Philippines, from many countries to to the Philippines, Thailand, and so forth, or in other cases there are projects that are trying to use public blockchain-like infrastructures to kind of increase interoperability between existing financial systems, basically by putting themselves onto a kind of hybrid, partially decentralized blockchain network. So, these are the kinds of things that people basically people in every specific kind of sector of any country should be probably looking into and seeing is there an opportunity in the particular place that I'm working at, right? So, basically I would encourage people everywhere to first of all learn what people in other places and people in other countries are doing, and seeing what kinds of problems they're trying to solve, and then go from there to seeing is this something that we can do, or alternatively actually come up with something kind of very fairly bold and new entirely, and kind of try yourself probably on a kind of small scale context and go up from there. The right thing to do, I think, whether actually even if you're in a kind of institutional context, so a government or a corporation, then the right thing to do, I think, is to find some fairly low-risk area to try things out first, and then kind of expand from there. And if you're an individual or a startup, then you would have a lot of freedom in kind of trying to see is there an opportunity that I can find and build something around.
Okay. Yeah.
I was wondering, what do you think of the direct acyclic graph around the IOTA protocol, and can solve the scalability and the energy consumption problem?
Okay, so my opinion. So first of all, directed graph technologies. Things like IOTA and Spectre and Ghost and so forth. They do have some value in particularly in reducing latency. So basically you can design systems where the latency goes down from something like Ethereum's 14 seconds, possibly to 1 second, with fairly low loss of decentralization. What they do not solve is, first of all, these things do not solve the scalability problem. Right now, I have entire 2-hour presentations where I talk about scalability in detail, but just to summarize, the reason why blockchain scalability is hard is because in all current designs on a blockchain, every computer in the blockchain has to process every transaction. In every single, no matter how your system is designed, if your system has this property, then the number of transactions that your system can process will be limited by the capacity of one single computer. This does not applies if you are building a blockchain. This applies if you are building a hash graph. This applies if you are building a Merkle dig. This applies if you are building some crazy spooky thing where you have like multiple layers of blockchains. Basically, if you have a system where you still have the issue that every node has to process every transaction, then you do not have what I would consider high scalability. Like so far, every hash graph based system that I've seen, even if it may succeed at improving latency, and it may succeed at somewhat improving the amount of by a small constant factor, the scalability you can do safely, it does not, all these systems do not manage to overcome this fundamental barrier. But well, that's the state of current technology. In 2 years, someone may come up with a fancy version of hash graph that solves problems.
Okay.
What's that? Yeah. Hey, Frank. I was going to ask, you explained a bit how mining works and how miners use electricity to solve problems to prove that these computers are actually there. Now that Ethereum is moving from proof of work to proof of stake, we spoke a little bit about that in Cancun, but I think it would be really interesting for people to hear what you think about it, proof of stake from a maybe economic, political, also kind of ethical point of view. So we also shed light on that new form of work.
Sure, yeah, that's a very good question. To give a brief introduction, the idea with proof of stake is that with proof of work, you can think about the kind of pathway of a miner like this. I have $10,000. I use $10,000 to buy some computers. I turn on those computers, and I run these algorithms to prove that I have these computers, basically by using them 24/7. And I can sometimes create blocks and get coins. Here's how proof of stake works. I have $10,000. I convert these $10,000 to $10,000 of Ether. I use this Ether, and inside of the Ethereum system, there would be a rule that lets me convert it into $10,000 of basically virtual miners. And then I can virtually turn on the virtual miners. And the Ethereum protocol simulates my ability to use these virtual miners to make blocks and get a reward. Now, in reality, I mean, it's very different from this, but this is kind of one simple analogy that can kind of illustrate the symmetry between proof of work and proof of stake. Now, if the reason why I personally, like proof of stake and always harp on and on about why I think it's better is several reasons. First of all, I believe that proof of stake is more secure and it is also more censorship resistant. So it's basically more difficult to attack. And the reason is that first of all, if you look at proof of work systems, Bitcoin particularly, something like 60%, 70% of Bitcoin hardware is produced in China. Now, as you probably know, the Chinese government is a sort of government that really does have the ability to fairly easily basically just come up with a decree one day and basically say, all of you miners are now belong to us, and we require you to attack the network. So, if there is at least one entity that has the power to basically make this entire network unusable for the entire world, because that's where the hash power and the ability to create hash power is concentrated. I mean, even independently of that, if any attacker has enough money and basically to buy up more computers than the rest of the network combined, then basically they can continue kind of wreaking havoc with the consensus until basically making blocks in the wrong places, making fake blocks, making empty blocks, doing various attacks, and basically making the blockchain permanently unusable. In proof of stake, basically you have the ability to create rules in the protocol that say something like, if you misbehave, then your virtual miner gets deleted. So we can create rules in the protocol that detect misbehavior and that automatically delete your virtual miner inside the system if you get caught misbehaving. And this allows you to basically have rules that say, oh, well, you totally can buy more virtual miners than everyone else combined, and you can make an attack. But if you make an attack, then all of your virtual miners basically get, basically digitally burn up, and the network keeps on going. And so if you wanted to keep attacking it, you would have to basically keep on burning money very, very quickly forever. That's the first reason. The second reason is a kind of more, social, economic, and environmental one, which is that this algorithm that with proof of work, where you prove ownership of a computer by basically using 100% of its CPU power 24/7 without ever stopping, is ultimately an extremely, economically wasteful one. Like, you're basically proving that you have a computer by using it to the point where you can't use it for anything else. So this, at this point, Bitcoin mining consumes more electricity than something like 153 countries. And so, in the context of, things like climate change and, people, every civilized country want to go into things like the Paris Agreement and so forth. I think that, it's going back to systems that require you, that basically involve proving that you have access to computers by burning huge amounts of energy are kind of somewhat a bit too retrogressive for my personal tastes. With proof of stake, on the other hand, because it's all digital, you can basically prove that you have a virtual miner just by signing a digital signature. So basically, with proof of stake, the costs of actually running and upkeeping the consensus become much lower. And so, like, in my view, that makes the system much more sustainable. Right? Like, basically, one of my concerns right now with proof of work is that it's like, I think the fact that we have cryptocurrency speculation and the fact that we have people, we have this big bubble where people are willing to just throw in billions of dollars of capital into the market every week, creates an environment where it feels like you can build a system that just burns billions of dollars a year, and it feels sustainable because the amount of new speculative money coming in every year is even more than that. But in the long term, if you build a system that relies on that forever, this is called a Ponzi. Right? Like, we do not want to build Ponzis, we want to build sustainable, decentralized economic systems. And so, like, if you want to build a sustainable system, then you need to have a system where the cost of consensus is much lower, and where the cost of participating in the system can be lower to the point where blockchains actually are competitive with traditional centralized architectures from a transaction cost perspective. Like, I think there are a lot of blockchain applications, for example, where you can, like, let's even look at something like decentralized Twitter. Would you be willing to pay an extra 50 cents a month in order to have a version of decentralized Twitter where your tweets are backed up by the entire world? Well, quite possibly yes. Would you be willing to pay $500? Hell no. So, like, I think that basically, like, reducing the cost of a blockchain is both a kind of moral imperative because economic efficiency is good and waste is bad, and like wasteful externalities are bad, and also a moral imperative because reducing the cost of the system is really critical to enabling this kind of wider scope of applications that we think will bring like a lot of societal value. So that's my general kind of reason for why I support, both proof of stake as well as why I spend so much time thinking about, like things like sharding and plasma and the various scalability improvements.
Okay. What are your opinions for digital identity applications on blockchain?
Okay, yeah. So digital identity I view as this kind of base layer that, if it's there, could potentially be used for a lot of different applications. So here's what I mean, right? So let's suppose that we had a smart contract on the blockchain, and the smart contract kept track of basically the public keys of a bunch of digital identities. And let's say actually this was 23 million digital identities, so basically every resident of Taiwan. Now let's say that you wanted to do a poll, and you wanted to do a poll of Taiwanese people and ask them what do you think about X, whatever X is, right? So then let's say you want to do this in a way that's kind of secure, and let's say you want to have a few properties. Number one, you want it to be secure, and you want to show that the results actually are trustworthy. You want to show that people are using real accounts and not fake accounts, and ideally you want to preserve privacy. So here is one thing you could do on a blockchain. So let's say that you have these 23 million identities that are part of the smart contract. What you can do is you can use a piece of cryptography called either a ring signature or zero-knowledge proof that basically proves that you have access to a particular one of these digital identities, without proving which one of these identities it is. And then to this proof, you can attach the message that says, I vote for A or I vote for B. Then you can basically take this, this transaction with this cryptographic proof and publish it. And then the system can basically just count all of the transactions that vote for A, all of the transactions that vote for B, and see how many people vote for each side. Let's say then that if we want to look at what the properties of the system are, right? So first of all, everything happens on a blockchain, and so the counting process is transparent. The process of you have the ability to verify that your vote is part of the total, and you have the ability to verify that, basically, all of the votes that people sent actually were included and considered. Then you have a guarantee of security, because if you have one of these accounts, then you can make one of these cryptographic proofs and you can vote. If you do not have one of these accounts, then you do not have the ability to make one of these cryptographic proofs. The cryptographic proofs can also be designed in a way that prevents you from voting twice. And there's a privacy goal that's preserved, because these cryptographic proofs, even though they prove that you have an account and they prevent double voting, they still do not reveal which particular account you voted from. And so what we have is a voting system that preserves anonymity, that preserves all of the security goals, and which actually is limited, and which can be limited to a set of people that actually represent real human beings. Right now, the last thing actually is kind of, I think, important, even in context going very far beyond just some poll that you'd want to take of the Taiwanese people, right? So, for example, there was a study that was released last week, I think, where if you look at all of the comments that were submitted to the American FCC about net neutrality, they found that something like over 80% of them were fake, right? 80% of them were basically written by a robot that took one standard script, we must, it is very important to, allow corporations to do whatever they want in order to preserve consumer choice, blah, 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 and so on and so forth. And they had basically a script that would just randomly replace a bunch of words with a synonym. And they sent like 10 million of these comments into the FCC. And they, eventually they managed to use basically fancy AI algorithms in order to kind of cross-check these against each other and figure out most of which ones were fake. But even still, basically there's this problem that whether you're talking about upvotes on Twitter, upvotes on Reddit, Twitter polls, online ratings on Yelp, any kind of system on the internet where you're trying to get some kind of feel of social consensus, that this can basically get incredibly easily and horribly manipulated. If you have a privacy-preserving identity system, then that's one possible way of solving this kind of problem. Right now, the point of this example, right, is that in order for all of this to work, you have to have certain base layer infrastructure. One of the important pieces of base layer infrastructure is that you have to have this kind of identity system that is either on the blockchain, or at least, it could be a system that's designed cryptographically off the blockchain, but could then be carried over onto the blockchain. And the blockchain can add some fairly important security properties, right? So, for example, one security property the blockchain can do is it can give you the ability to revoke any identity immediately. So you can basically you have a list, and whoever manages the list just immediately has the ability to remove anyone from the list if they discover that that identity is fake. So you have this identity as a base layer. Then on top of this identity as a base layer, you can then do things, you can add a bit of cryptography, and you can do privacy-preserving identity. Notice that in order to add this kind of second layer of privacy-preserving identity, the system that the original identity system did not have to cooperate at all. It just had to exist, right? So if identity exists as the base layer, then this other thing can be built on top of it, this other thing can be built on top of that, and suddenly you have basically much better, more trustworthy, more reliable systems for measuring social consensus. So this is one application. Another application would be that, in general, if you look at things in, let's say, basically any kind of system where you want to limit the number of accounts that one person can have. Well, great application for privacy-preserving identity. Let's say you wanted to look at financial applications. in financial applications, there are often regulatory requirements to do things like restrict some system to some particular set of users. Let's say you want to sell, I don't know, alcohol, and you want to limit it to people that are over 19. Let's say you want to create a financial system, and in order to reduce your regulatory requirements, you would want to let's say limit the size of everyone's accounts to $30,000 or whatever the threshold is here. Then you could use blockchain-based identity systems and basically automatically hook into that, and basically let people just very quickly prove basically who they are, that they are, or that they are a member of one particular set, and just do all of this very quickly and immediately without having to go through a process to verify your identity each time. So that's another example of the kind of thing that you can do. The other thing that you can do is that one of the benefits of blockchain-based what are called self-sovereign identity paradigms particularly is that you can have an identity and a reputation where this identity and reputation are not controlled by any one particular central service. Right? So one example of this is that if, let's say, you are a driver and you are using Uber, and at some point, let's say you decide that Uber is just exploiting you way too much, if the algorithms are paying you below minimum wage, whatever, and you want to say, screw you, I'm switching to Lyft. Well, one of your problems is that if you switch to Lyft, then your rating basically starts from scratch. Well, what if you could have a rating that is not hosted by one particular company, and instead is basically hosted kind of in the cloud, just consisting of a set of cryptographically signed messages that people have made about you? Well, this is the sort of thing that could theoretically be done with the help of a blockchain, right? And you could imagine, basically, the idea of self-sovereign identities is that these are identities that are issued by yourself, and then everything else about the identity is just an assertion that's made by some other account. So you have an assertion that would be signed by some government that says you are a citizen of your country. You could have an assertion signed by another identity that says, oh, this is an outstanding person. I bought a laptop off of him on eBay, and he actually delivered. You could say, oh, this particular person made took a loan and managed to pay it back, and so on and so forth. And basically, you would have this kind of decentralized alternative to things like a credit score plus plus rating system, right? So this is one example. These are all examples of the sorts of things that could potentially be done if you have either blockchain-based identity or kind of blockchain-friendly identity as a base layer.
Okay.
We all know that the cutting edge of technology of internet bloomed in the 1990s, and then the dot-com bubble burst, and companies died, leaving good companies like Google to live on and changing the world. Do you think that the history will repeat itself in terms of ICO or cryptocurrency?
Yeah, so I think that there already have been bubbles, and there will continue to be more bubbles, and yes, there will be painful periods where these bubbles will burst. At some point, Bitcoin will drop by more than 2/3 again, and at some point, if you put all your money into Bitcoin, thinking that it will keep going up 10% every month forever, you will cry. You can do the same thing with Ether. You will also cry. So, first of all, bubbles exist, and the thing with cryptocurrency is that bubbles do happen, and they will continue happening. But a bubble is never just a financial bubble, right? A bubble is not kind of a unique failing that only exists in the context of financial capital markets. A bubble exists also in kind of social contexts where people get overexcited about some particular thing, and they get more excited because everyone else is excited, and at some point people realize that something is overhyped. And these kinds of bubbles exist too, right? So I talk about lots of blockchain applications, and it may well be the case that there are very good reasons why something like more than half of them will just never end up turning out to be anything interesting. That's okay. It is okay to be very excited about something that has a 20% chance of changing the world and an 80% chance of being a complete dud. So, because changing the world multiplied by 20% is still on average an extremely huge contribution to society. Now, the thing, so like it's, I think that from the, I mean, there definitely are a lot of companies that I personally, I'm not going to try to name too many names, but I do think there are companies that have raised very huge amounts, and like both inside the ICO space and outside of it. Like one of the things, the crypto space has convinced me that I don't think ICO ICO participants can be stupid, but the reality is the traditional world isn't that much better. Right, there have totally been $100 million from like supposedly very professional VCs and big multi-million-dollar companies that have invested into traditional companies, like with like legal agreements, like safes, fully regulatory compliant, whatever. That in my personal estimation are total crap, and in the estimation of history so far are also total crap. So like these things will happen. And lots of these things will happen. There will be plenty of pets.com instances on the blockchain. I mean, I say this somewhat ironically because 2 days ago there was a project on Ethereum launched called CryptoKitties. But I mean, I like CryptoKitties. Hopefully we'll be more better than pets.com. But basically, I would say that if just never ever put 100% of your faith into something, and never ever put 0% faith into something. And you'll never be too disappointed, and you'll have a fairly realistic perspective. And
好，因为时间关系，开放最后一个问题啊。刚刚那学长先举手。对，就你不用回答。来自。
Hi, Vitalik. As we know, the China government just prohibited some digital currency transaction 2 months ago. And what's your opinion about the influence to the whole digital currency transaction environment if the China government keep reinforcing the limitation?
Yeah, I mean, I would actually say fairly little. Like, it's, so first of all, I believe China required Apple to remove Skype from their App Store a few days ago. This has not led to a global crackdown on Skype, right? So it's I think in the case of China specifically, I actually do think that at this point the world has kind of basically mostly already priced in kind of both financially and psychologically the idea that they're going to be fairly unfriendly to at least at least kind of cryptocurrency and public blockchain financial applications. I mean there's still possibly hope in some of the other areas, but I don't think that this leads to, or even necessarily will, lead to similar ones in the rest of the world. So that's that's kind of one thing. Now, I mean, obviously, I mean, it has influenced the markets because China is the home of a lot of mining and a lot of trading, and I mean, so far. Some of the trading has managed to find a way to come back, and the mining has continued. But I think that even without that, there are alternatives. And if you look at even just crypto markets, like Japan and Korea and so forth are picking up very quickly as well. As far as kind of public blockchain cryptocurrencies go, as far as public blockchain non-cryptocurrency focused and consortium chain applications, I believe that my personal impression is that kind of the public and institutions and regulators do already kind of understand that these two things are in some ways kind of separate spaces, and that even the ones that are not very friendly to cryptocurrencies are still totally fine with things like using blockchains to create more secure decentralized polling systems. So I think that those things do have those things do have in my view a bright future even if cryptocurrencies don't. Though I do think that some level of cryptocurrency accessibility is necessary in order to, basically fulfill kind of the crypto-economic, actually make the crypto-economic side of an open public blockchain work. So, it is possible that crackdowns on cryptocurrencies will push, in those countries that implement them, will push other applications more toward private chains rather than public chains than I think is appropriate, which is something that I think is worth watching out for. But otherwise, I mean, I think that it's like the important thing is just that so like in most places, including if there hasn't been a crackdown yet, and like a lot people, like the regulators in a lot of places, don't even see a reason to go that far, make a crackdown. In fact, in contrast, in Japan, they recently gave 11 licenses to digital to cryptocurrency exchanges there. So I think that like there are many different roads to take, and I have a lot of hope that many parts of the world will take a favorable road.
那我们在 Vitalik 离开之前，我们先请我们台大资管系教授曹承柱曹主任，他也是台大数位未来研究中心的主持人。上个礼拜才办过一个 Blockchain POC 的一个讨论会，那我们欢迎曹老师来为我们做一个 conclusion。谢谢。
Well, I don't think I'm going to make